Swayam Prabha. Digital India. Educated India.
We will continue our discussions on spatial kinematics of rigid bodies. We will just recapitulate what we have discussed in the last lecture about kinematics in 3 dimensions and the prototype problem which represents rotation about a fixed point, and we are going to look at some problems. Recall that we had discussed this example, this prototype system of an axisymmetric body rotating about a fixed point. We had set up the coordinate system x y z, x naught, y naught, z naught is the inertial coordinate system which is fixed. The body is rotating about the origin of this x naught, y naught, z naught frame. It has got a spin angular velocity omega s about its axis of symmetry. Then we had discussed the construction of this x axis as a cross product of z naught and z, and the rotation of the frame about this axis, this x axis, is the nutational angular velocity, and there is a precessional angular velocity omega p which is about the capital Z naught. The angular velocity of the x y z frame, which is the frame angular velocity omega f, is due to the precessional motion about the z naught axis and the nutational motion which is the rotation about the x axis. And remember, this x axis always lies in the x naught y naught plane. The total angular velocity of the body is nothing but the angular velocity of the frame plus the angular velocity of the body with respect to the frame. Therefore, it is omega p plus omega n plus omega spin omega s. Angular acceleration, to find out angular acceleration we have to use this prescription d dt is del del t, which is a local derivative, plus omega f cross. Del del t represents the local time derivative, which means it is the magnitudes of the various vectors, not derivating the frame vectors themselves. Therefore, del del t is the local derivative as observed by the local observer, and because of the frame rotation we have acceleration or total rate of change of a vector with respect to time, which is given by omega frame cross, and we had used that to find out the angular acceleration of the body by derivating the angular velocity of the body, and also found the angular acceleration of the frame. Everything followed this prescription of d dt is equal to del del t plus omega f cross. Let us now move on to a problem. This is from the book of Merriam and Craig Dynamics. A vertical shaft and attached clevis rotate about the z axis at a constant rate capital omega equal to 4 radian per second. Simultaneously, the shaft B revolves around its axis OA at a constant rate omega naught is equal to 3 radians per second, and the angle gamma is decreasing at a constant rate of pi by 4 radian per second. Determine the angular velocity omega and magnitude of angular acceleration alpha of shaft B when gamma is equal to 30 degree. The x y z axis are attached to the clevis and rotate with it. This is the clevis. Whenever you are asked to find out, determine the angular velocity and angular acceleration of the shaft, it would mean it is the absolute angular velocity and angular acceleration. The xyz axis is fixed to the clevis and it is oriented like this, that z is in the vertical direction, x is the direction about which the shaft is changing its inclination, and y axis completes the right handed coordinate system. We will use this coordinate system x, y, z. Now, note we have shifted away a little bit from our frame that we were using for our prototype problem. Now, this frame is a rotating frame, of course, because it is rotating with the clevis at an angular rate capital omega. However, it is not attached to the body or to the axis OA, therefore, gamma, the change of angle gamma is not reflected in the rotation of the frame. The frame is rotating only because of the rotation of the clevis about the vertical axis. Let us express these vectors in the frame we have chosen, the x, y, z frame. The frame angular velocity is straight away 4 k cap radian per second, because it is along the z direction, omega is about the z axis, therefore, it is 4 k cap radian per second. Because of the change in gamma, there is an angular velocity of the axis and hence of the body. Now, omega gamma, because of change in gamma, is gamma dot I cap, that can be very easily seen, and that turns out to be minus pi by 4 I cap radian per second. Why minus pi by 4? Because it was specified in the problem that gamma is decreasing. Gamma is decreasing at a rate pi by 4 radian per second. Therefore, the angular velocity is minus pi by 4 I cap radian per second, and this is of the this axis OA. Now, omega naught, which is the spin angular velocity vector, omega naught is the spin angular velocity vector, which is shown, is minus 3, which is the 3 radian per second was the magnitude, and the direction is given by the unit vector OA, this direction, this unit vector direction, which can be expressed in the x, y, z coordinate system. I have done that. It is cos gamma j cap, this is gamma, therefore, cos gamma j cap plus sin gamma k cap, and the spin is taking place in this direction, you can see here, and therefore, it is minus 3 times unit vector OA. This is nothing but the unit vector OA. Now, therefore, I can write the angular velocity of the body, the net angular velocity of the body B. Omega B is omega frame plus angular velocity with respect to the frame. Now, with respect to the frame, there are two contributions, omega gamma and omega naught. Omega naught is the spin and omega gamma is the change of the rotation of the axis. Therefore, net angular velocity is omega frame plus the angular velocity relative to the frame, or as seen by the local observer. You plug in these values, these vectors that we have derived or written down, and we get the net angular velocity of the body of the shaft, and you can find out the magnitude of course. Now, angular acceleration of the body is nothing but the time derivative according to our prescription. It is del t of omega body plus omega f cross omega body, and del omega body del t is del omega naught del t. If you substitute all these expressions in the expression of alpha of the body, then you will finally get the angular acceleration of the body. Here I must mention something. When you calculate the local change, local time rate of omega of the body, you see omega of the body is this expression. Let me write it down. Omega of the body is equal to omega frame. Omega frame is 4 k cap radian per second plus omega gamma, which is gamma dot I cap, plus omega naught. Omega naught is minus 3 cos gamma j cap plus sin gamma k cap. When you take the local derivative of this vector, local derivative means which does not derivate the frame vectors. For this is a constant, this is a constant, therefore, its local derivative is 0. Gamma double dot, now that is 0 because it is decreasing at a constant rate of gamma dot pi by 4 radian per second, therefore, that also does not get derivated. But then the third term, if you look at the third term, when you take the local derivative, it is minus 3, and when I take derivative of cos gamma, it becomes minus gamma dot sin gamma j cap plus gamma dot cos gamma k cap. Therefore, in this problem we do have a local time derivative of omega body, and that is given by this, and that is why I wrote this statement, and this is what we get from the data that is given in the problem. At 30 degree we have to calculate, when gamma is 30 degree we have to calculate the angular acceleration of the body, and this is how we get the local time derivative of omega b, the angular velocity of the body. You can calculate the magnitude of the angular acceleration, it is 11.44 radian per second square. Let us move to the next problem. A right circular cone A rolls on the fixed right circular cone B at a constant rate and makes one complete trip around B every 4 seconds. Compute the magnitude of the angular acceleration alpha of the cone A during its motion. Now, this is a problem of one cone rolling over a fixed cone. This problem will we will encounter this problem or these kinds of systems where a cone is rolling over a fixed cone in later lectures as well. You have to remember that the cone A is rolling without slipping on cone B, and there is a line contact between these two cones, and this line contact goes like this. This problem might look slightly hypothetical because it is very difficult to find cones rolling over a cone rolling over another cone, but then I will show you how this problem is relevant in various problems of rotation of a body about a fixed point. We have to calculate the magnitude of angular acceleration alpha of cone A, but before that we have to also calculate angular velocity. It is given that this cone, while this is rolling suppose like this, it goes round and completes one trip in 4 seconds. Let me fix up a coordinate system x, y, z like this. I take z axis as the spin axis of cone A. I have marked here, z axis is the axis of spin of cone A, and this is the side view of the same system. This is the z axis, which is the axis of spin, and y axis is perpendicular to the z axis, but in the plane formed by z and z naught. Z naught is an inertially fixed direction, which is the axis of the fixed cone, and x therefore must come out of the plane of the screen. It is perpendicular to y and z and coming out of the plane of the screen. Now, we are going to express everything in this x, y, z coordinate system, which is of course a rotating frame. You can use geometry to find out various angles. This angle phi, for example, this angle phi can be determined from the geometry that is specified. Now, we are going to express all the vectors. Omega is the precessional angular velocity. This is how the spin axis is rotating about the inertially fixed z naught axis. This angular velocity is capital omega, and capital omega is the magnitude of omega times the unit vector expressed in x, y, z frame. Therefore, I have to represent this unit vector. This unit vector, let me call it z naught cap, and this unit vector is exactly that, z naught cap, and this you can find out from geometry. This angle phi is 13.63 and this is 45 degree, and therefore, that angle is 58.63 degree. Z naught makes an angle of 58.63 degree with z axis. Now, it is easy to represent the unit vector in that direction then. Now, the magnitude of omega, capital omega, is given in terms of the time it takes for the small cone to make a complete trip around cone B, the fixed cone. It covers 2 pi radians, in 4 seconds. This axis covers 2 pi radians in 4 seconds. Therefore, this omega magnitude must be 2 pi by 4, that is pi by 2 radians per second. And this also happens to be the angular velocity of the frame. This is how the frame is rotating. Now, the spin of the smaller cone, the cone A, let me express it as the vector p, which I have shown in the figure, and we do not know its magnitude as yet, but we know that its direction is in the k cap direction. Therefore, I express the spin of the smaller cone, the cone A, by the p vector is equal to p times k cap. We do not know what is the magnitude of p, but what we know is the no slip condition between the two cones. There is a no slip condition between the two cones. How to use that? First, we find out the net angular velocity of the smaller cone, the cone A. How do I find out? It is the frame angular velocity plus the angular velocity of cone A with respect to the frame, which is the spin angular velocity, and that is what I have written here. The net angular velocity omega of cone A is the spin angular, the frame angular velocity plus the spin angular velocity. Now, we are going to write down velocity of a point on this contact line. As I mentioned that there is a contact line between the two cones. I take an arbitrary point on that contact line. I have taken this end point, the point on the edge, this point P, and I express the velocity of point P using kinematics. Therefore, we are trying to express the no slip condition at P, no slip condition for cone A at P. P is a point belonging to cone A. Velocity of point P in terms of convenient point, O is a convenient point whose velocity I know is 0. Velocity of P is equals to velocity of O plus omega cross OP. There is no VREL because O and P belong to the same cone, cone A. There is no VREL. Therefore, velocity of point P is equal to omega cross OP, and that must be 0. Velocity of O is already 0, therefore, omega cross OP must be 0. This is the no slip condition. And what does this tell us? Omega cross OP is 0 when are two non-zero vectors, the cross product of two non-zero vectors is 0, when either they are co-oriented or oppositely oriented. In other words, the angular velocity, the net angular velocity of cone A is along OP. This is a very important conclusion that we draw from here, from the no slip condition. The net angular velocity of cone A is along OP cap vector, the line of contact. It is along the line of contact between cone A and cone B. Therefore, omega must be some magnitude times OP cap, the unit vector along OP. Now, OP vector I can represent very easily. I have this angle phi, I can represent this vector in xyz, which I have done, and omega cross OP, this is omega cross OP's expression. I have done this algebraic calculations. You can easily do this and put that to 0, and if you do that, from here you can solve for P, and that is P equal to 4.724 radian per second. Therefore, this spin speed of cone A is determined from the no slip condition on the line of contact, and once I know P, the net angular velocity of cone A is completely determined. It is given by this expression. If P is known, I know omega completely. Okay, so we have P, we have expression of omega. I have removed the derivation steps. Now, we have to find out the angular acceleration. This was our objective, to find out the angular acceleration of cone A, and angular acceleration of cone A is nothing but total time derivative of the angular velocity of cone A. There is a temporal time derivative del t of omega, which is 0, all the coefficients of I cap, j cap, k cap are constants, and what remains is omega frame cross omega. Omega frame is nothing but capital omega, I have mentioned this, and net angular velocity of the cone A of the body, which is cone A, is omega plus p. Omega f is nothing but omega, and therefore, if you take this cross product, it simplifies to omega f cross the p vector, which turns out to be minus 6.33 I cap radian per second square. This is the angular acceleration of cone A. So, that completes this problem. To summarize, we have discussed the kinematics in 3 dimension, we looked at the prototype problem, and whatever examples that we have discussed, they all fall under that prototype system, which is an axisymmetric body rotating about a fixed point. You should remember how the frames were constructed. There is of course no single way to construct the frames, but we have taken problems in which we have constructed frames in a different way. So, whatever you do, you have to identify what is the frame angular velocity, the spin angular velocity, and nutation, etc., the other angular velocities, and expressing those you can find out angular velocity, net angular velocity of the body, angular acceleration of the body, angular linear velocity and linear acceleration of any point on the body, and all these things we have demonstrated through example problems. So, with that I will close this lecture.